Hello, welcome to our channel for probability and statistics. In this video, we will talk about probability distribution of one-to-one transformation of continuous variables. So suppose x is a continuous random variable with probability distribution fx. So let y equals ux, which is a one-to-one correspondence between the values of x and y. So that the equation y ux can be uniquely solved for x in terms of y. So x equals wy is the inverse function of x in terms of y. So we want to find the probability distribution of y from the given distribution of x. So the solution is the probability distribution or density of y equals fwy. So f means the probability distribution density of x, but here in the brackets we fill in wy. So here x using wy, the inverse of x in terms of y. So this fwy is the density function of x, but we use y values here. Then we have 2 times and a matrix called J. This J is the derivatives of wy. So wy is a function, inverse function of x in terms of y. So from this function, we have to calculate the derivative of x in terms of y. So this is also called the Jacobian of transformation. So the density of gy is f, the density function of x, fill in with the inverse of x in terms of y, then times the value of this matrix of J. This J is the inverse of x in terms of y. So we take a look at an example to get more illumination of this formula. So say x be a continuous random variable with probability distribution fx equals x divided by 12 for the x value between 1 and 5, and 0 for other values. So the question is, find the probability distribution of the random variable y, which is 2 times x minus 3. So the solution is, so we can get the inverse solution of y equals 2x minus 3. We'll get x equals y plus 3 divided by 2. So this is a one-to-one transformation, because for each value of x we can get a unique value of y, and it definitively has a one unique value for y. So this is a one-to-one transformation. Then we can get the Jacobian. Jacobian value is dx by dy equals 1 of 2. So from this expression, we take derivative to y. So equals 0.5. So therefore, and this value's matrix value is also 1 of 2, right? So therefore, we can find the density function of y to be, we just fill in to the formula. So the distribution of x, but take the y value here, then times the Jacobian value. So the result is y plus 3 divided by 48. So the y bounding value is minus 1 to 7. Then for the density of y is 0 for other values. So for the one-to-one transformation, we can also extend to more than one variable case. So suppose that x1 and x2 are two continuous random variables with joint probability distribution f x1, x2. So if we let y1 equals u1, x1, x2, and y2 equals u2, x1, x2, also a one-to-one transformation between the points x1, x2, and y1, y2. So the equations y1 equals mu1, y2 equals u2 can be uniquely solved for x1 and x2 in terms of y1 and y2. So the inverse function is x1 equals w1, y1, y2, and x2 equals w2, y1, y2. So the joint probability distribution of y1, y2 can be got from the distribution of f. Here f is the joint distribution of x1, x2, but here we just fill in the inverse expression w1, w2 in terms of y1 and y2 in the bracket. And similarly, we also times the matrix value of Jacobian. So here the Jacobian is a 2 times 2 dimension. The Jacobian is the partial derivative of x1 by y1 and the partial derivative of x1 by y2. And similarly, here is x1, x2, y1, and x2, y2. So say, for example, partial derivative here, which means x1 equals w1 y of y1, y2, right? So we just take y2 as a constant. Then this expression, then take the derivative with respect to y1. And similarly for the other part in the Jacobian. So we just calculate matrix value of this matrix determinant of this Jacobian matrix. So we also take a look at an example. So x1, x2 be two continuous random variables with a joint probability distribution. The value is 4 times x1, x2, and the bounding value is 0 to 1 for x1 and 0 to 1 for x2. So the question is find the joint probability distribution of y1 is x1 square and y2 is x1 times x2. And the solution is the inverse function we can calculate is y1 equals x1 squared, y2 equals x1, x2. The result is x1 equals square root of y1, and x2 equals y2 divided by square root of y1. So from these two inverse functions, we can get the Jacobian is here is the partial x, partial y1, then partial x1, partial y2, partial x2, partial y1, and a partial x2, partial y2, right? So the result of this matrix determinant is 1 divided by 2 times y1. So we just fill in the formula, we'll get the joint density for the y1 and the y2 equals the joint density of x1 and x2 with the y1, y2 value here, then times the Jacobian determinant. So the result is 2y2 divided by y1. And the bounding area is look like this. So from this mapping, from x to y, we'll find that this is the x bounding value and this is the y bounding value. Thanks for watching.